Okay, so here's just a few concepts of the chapter on physical and chemical change that might be confusing. So I just quickly want to say that you know that we have pure substances, and pure substances are substances that's always the same. So those would be elements and compounds. Okay, so a compound, for example, is something like calcium carbonate, where we always have one calcium bonded to one carbon bonded to 3 oxygens. Okay, so that's a compound. Elements like sodium or like chlorine. Chlorine is one of the 7 diatomic elements, so we write it as Cl2. Okay, then an impure substance would be a mixture of something, like, for example, a coffee. Some people have coffee with 1 spoon of coffee and 1 spoon of sugar and a bit of milk, and some people don't take any milk in it with 3 spoons of sugar. But both people, even though the mixture differs, it's still coffee. Okay, so that's an impure substance. It's a mixture where the composition can be different for the same mixture. Okay. Now, when they ask you whether a certain change is physical or chemical, you need to look at whether that change changes compounds. Does it make a compound something completely different? For example, does it break that compound apart? Like calcium carbonate forms calcium plus CO2 or whatever. Okay, so if that happens, then we don't end up with the same thing we had in the beginning. Then we have a chemical change. Okay. If we have a physical change, then what that substance is doesn't change. So, for example, we have water that is a solid, so it's ice, and that ice melts to form water in a liquid state. So what this is and what this is doesn't change. So if the actual substance, the pure substance, doesn't change, it only changes state or condition, then it's a physical change. But if what the substance is changes, then it's a chemical change. Okay, the second thing that I just quickly want to talk about is the laws of chemistry when chemical change takes place. Now we have the law of constant composition, the law of conservation of mass, and the law of conservation of mass exists because of the law of conservation of atoms. Okay, so atoms are conserved in a reaction. That's why mass is conserved. But I just quickly want to explain this. Constant composition means that if you have calcium carbonate in South Africa and you have calcium carbonate in China, that's going to be 1 calcium bonded to 1 carbon bonded to 3 oxygens, always. If you have water in South Africa and you have water in China, In South Africa and in China both, you will have 2 hydrogens bonded to 1 oxygen. So constant composition means the composition, what a substance is composed of, is always constant, always the same. Okay. Conservation of mass, I'll come back to now. Conservation of atoms means that every single element you put into a reaction, you have to also get out of the reaction. So if you have, for example, nitrogen that reacts with nitrogen and hydrogen, and then the product will have nitrogen in and it will have hydrogen in, and it will only have nitrogen and hydrogen, because you can't all of a sudden have some new element here that you didn't have here. Okay, so for example, if calcium carbonate decomposes, it will decompose into calcium and carbon dioxide. On this side we had calcium, there we have calcium. Here we have carbon, there we have carbon. Here we have oxygen, here we have oxygen. So we won't have, let's say, lithium all of a sudden here, if we didn't have lithium here. So conservation of atoms means all of the atoms that we have as reactants, we will also have as products. So nothing will get lost, and nothing will all of a sudden appear. Okay, that's the conservation of atoms. But now the conservation of mass happens because we have conservation of atoms. So in other words, if you have 2 nitrogens on this side, you're going to have 2 nitrogens as products. If you have 6 hydrogens on this side, you're going to have 6 hydrogens on this side. So that's where balancing comes in. So we balance an equation so that we have conservation of mass as well. Because 3 hydrogens is 3 times the mass of 1 hydrogen, right? So if we balance, then because we have 3 hydrogens there, we need to get the same amount of hydrogens on this side, so that the masses, the total mass left, equals the total mass, right? So by balancing, we make the masses left and right the same. So there we have 3 times 2, 6 hydrogens, 2 times 3, 6 hydrogens, 2 nitrogens, 2 nitrogens. And this total mass will be equal to this total mass. So what we do to prove the conservation of mass is we balance. Well, firstly, we balance conservation of atoms, we balance, and then we prove that balanced equation by calculating the molecular mass on both sides. Okay, so how we prove that by calculating the molecular mass on both sides is, let's say, for example, we take this one. Yeah, nitrogen has a molecular mass of 14, but there's 2 of them. So that's 2 times 14. And this molecular mass of nitrogen plus the molecular mass of 3 hydrogens, and on that side, the molecular mass of 2 times NH3. Okay. So, yeah, we have hydrogen has a molecular mass of 1, and there's 2 there, but there's 3 of this diatomic molecule. So 1, 2, 3 of them. This hydrogen weighs 1 gram per mole, that one 1 gram per mole, 1 gram per mole, 1 gram per mole. Okay, so that's what this means. This means 3 sets of 2 hydrogens each. Okay, so to calculate this total mass, that's going to be 3 times 1 times 2. So that gives us 6 grams per mole there. Six grams per mole is our total molecular mass of that hydrogen. For this nitrogen, our molecular mass is going to be 28 grams per mole. Yeah, our molecular mass is going to be 2 times nitrogen, which is 14 grams per mole, plus 3 times hydrogen, which is 1 gram per mole. So that gives us 14 plus 3 is 17 times 2 is 34 grams per mole. So now the NH3 on this side is 34 grams per mole, and on this side, if we add 28 plus 6, it also gives us 34 grams per mole. So yeah, we have 34 grams per mole on the left side, 34 grams per mole on the right side. So we've proven the conservation of mass. And the way we get the mass to be the same is by balancing. Then next, just a reminder of how balancing works. If we have this reaction as an example, the first thing we do is we separate the reactions from the reactants from the products. Then we write a list of each element. So we have copper, we have carbon, we have oxygen, hydrogen, and chlorine. And we count how many we have to start with. 1 copper, 1 carbon, 3 oxygens, 1 hydrogen, 1 chlorine. On this side, we write them in the same order. We know the law of constant atoms says that all the atoms that we have left, we will have, right? So copper, we have 1 of. Carbon, we have 1 of. Oxygen, 1, 2, 3. Hydrogen, 2. Chlorine, 2. Right. Now, to balance, we want the same amount of each one of these elements. So here we have 2 hydrogens and 2 chlorines. Here we have 1 and 1. So we're going to add a 2 in the front of this HCl, which is going to make this hydrogen 2 and this chlorine 2. And now all of the elements are the same left and right. So that reaction is now balanced. Okay, so that's how you balance a reaction. Okay, the last thing I want to remind you of is how we write formulas for a compound, for compounds. All right, so for this, you need the periodic table. So let's say, for example, we have let's make it magnesium and nitrogen. Right. Now, on the periodic table, you need to look at what group magnesium is in, and magnesium is in group 2. So then in pencil, you write there magnesium is in group 2, so that's +2. Then you check the group of nitrogen. Nitrogen is in group 5, and group 5 always has a charge of -3, so you write the charge there. Then, in order to write this compound, you cross over the charges. So this compound is going to be Mg3N2, and you throw away the plus and the minus. Okay. So that's what you do if those charges differ. If the charges are the same, let's make it magnesium and oxygen. For example, magnesium is charged +2 and oxygen is charged -2. Now, before we cross them over, they cancel out because they are the same. So this compound will be written only as MgO. Okay. Third thing is if we have something with a charge of 1, let's say magnesium with chlorine. So magnesium has a charge of +2 because it's in group 2. Chlorine is in group 7, so it's -1. Now we want to cross over these numbers, but we never write a 1. So because we don't write a 1, that's going to be Mg, nothing, chlorine 2. Okay, so we don't write a 1. Yeah, you have to remember if they are the same, they cancel. So we won't write anything that was crossed over. There, because they differ, we cross them over. Okay, last thing is if one of the compounds is a transitional metal. So transitional metal, the transitional metals are all in the periodic table between group 2 and group 3. So these are all transitional metals, and they can be charged +1, +2, or +3. So for them, we need to, when we write a name, we need to specify which one it is. Let's take, for example, nickel. So nickel, if it bonds to, for example, oxygen, nickel can be charged either +1 or +2 or +3. Oxygen is always -2 because it's in group 6. So in all the cases, the numbers cross over. But for the first case, because it's a 1 that crossed over, we don't write that 1. We just write the 2 that crosses over. At this one, because the 2's are the same, they cancel out, so nothing crosses over. Well, nothing is written because they were cancelled. Yeah, that 2 crosses over, that 3 crosses over. They are not the same, so they don't cancel. There's no 1, so we have to write both of them. Okay, so that's how you write a formula.